So in this video, we want to talk again about the three most important procedural data generators, I think I can call it. And those are the randomness, the noise, and the Curlnoise functions. And they are kind of overlap actually to an extent, but it's, in my opinion, a good idea to kind of think of those three as three use cases when you need some kind of computer generated data. So the first thing is randomness, and what we've already seen is when I do something like this, I get completely random colors, and those are actually random for every single element of my vector here. So as you can see, this is one random that is going into a vector, but it actually creates three random numbers because it's a vector. So this, when we look into the help again, you can see that the rand function actually can return multiple results, data types, so float and vector. And this is called polymorphism. To be more precise, I think this is overloading a function, because someone started a discussion with me once about this, but the overall term for this is still polymorphism, as far as I know. But anyway, you can see that the same function can give back multiple things. And in this case, it understood that it is a vector, therefore it gives back a vector. If I want it to be a single number, so that if I want to have black and white as a feedback, then I just do an explicit typecast and turn this result into a float, or actually tell the rand, so to say, that it should return a float. So this should make sense. We've seen that before. Now, I tend to use rand most of the time because I'm lazy. There's also random, and technically they're not completely the same. As you can see, if I switch from rand to random, I get slightly different results. But the difference is when we look into the help, the random function is different to the rand function in the way that the random function is technically a space-dependent function. So you could actually put a position into this. As you can see here, the input is actually expected to be a position. I actually don't use that very often. If that interests you, or if you have kind of more knowledge in programming, then you can probably have more use case for this than me. But I only separate between rand and a noise. And if I sometimes use random, even though technically it's not completely correct, I put in the point number, and then I also get kind of similar results of random result per input. And this is really what I care about. And as you know, to understand all this, it makes sense to see the different result that I get based on a noise function. And here you can see, and let's turn this into a float as well, that the difference is that it's not completely random, but it is based on a pattern in space. And this is why the usual input is a position. And what can make sense here is to change the size based on a parameter. And this is what I usually do. And actually this time we can get rid of the float to show this. So what I use very often as a standard setup, and you will see that throughout the course, is I build the noise with a position as an input. And even though it's a bit weird, since it's based on the position sampling, you change the size of the result by changing the size of the input, as you can see here. And usually I divide by a size because it's more natural to what we would expect. If you lower the size, then the whole detail gets smaller. If you increase the size, the detail gets bigger. And this is why I do it this way, even though a multiply obviously would work as well. It's then just inverted, and I found this sometimes a bit confusing. And this is why I divide it. And then, of course, as we know, what comes out of noise, just like with random, is between 0 and 1, so it's normalized. So what you usually do is you multiply the result, and this would then be the amplitude of the result. And by the way, I call this size, but you could also call this frequency. A lot of people would call this more correct. So let's actually do this time. And funny enough, and let me quickly delete my size parameter. And funny enough, we have a data conversion problem. Surprise! And that comes from the fact that the amplitude here is a float. So what I could have done is, instead of float amplitude, I turn this into a vector parameter. So let's quickly delete that parameter so that I can rebuild it. And then I have the advantage of being able to scale the different elements, RGB in this case, separately of another, which can result in something like, okay, if I want more red to be part of this, I can increase the amplitude of the red channel. This is one way of doing it, but sometimes you don't need that, even though it's really helpful to have it. But then you could also just take instead a float channel or parameter and convert it explicitly or cast the data type explicitly to a vector. So let's delete this again so that I get a float controller, and then you can see that this works as well. It just multiplies the result as a vector, so the end result will be a vector as well. Yay, data type conversion problems. So this is a common setup you will see. And then also what I sometimes do is I add something to the position, and just quickly, let's do this with time actually. So if you add something to the position that is the input of the noise, then the whole thing will move in this direction. And this kind of moves in this direction here in the vertical, actually in this direction technically, because it's a single float number that is added to a position, which in this case should result in a float as well. For some reason it doesn't. This is now converted explicitly or implicitly to a vector. What am I talking about here? Since this is a position, actually this is the offset, and you can put this, and so it makes sense to actually use an offset vector. And when you do this, you can actually control the directions more clearly. For example, I could say, please only move in the X direction, and then I would use the time here in form of an expression so that only the X element of the position is changing, not all three. And this is often a very good idea for all kinds of noise functions, because in this case, I might want to see the direction of the change, or I want to give it a specific direction, for example, 45 degrees in X and Z, so something like this direction, and I can explicitly, okay, in this case, have to invert that so that it's the opposite direction like this. And here you can see, and this way I can explicitly say which direction the movement should be, or in a specific case like that, where the y-axis is basically not visible, or there's no area that the y is covered by, then I can do what I already know from the mountain function, and that is to put the current time in form of an expression into the y element, and then it seems like the whole thing is warping around. Now, this shouldn't be completely new to you, but I just wanted to kind of bring together all the different techniques that we've seen so far. One last thing, of course, you could have used a vector for the frequency as well and for the amplitude. So let's quickly do this by deleting the two and rebuilding them. And this would simply have the advantage of being able controlling those three elements separately. So you could say, okay, I want more red in the color and less green. And also I could have deformed the noise in one direction and less in another. And this way I can stretch things. And this especially makes sense when I have geometry to deform, so that I can deform the noise. Not really surprising. Nonetheless, all of this is kind of something I just think it's important to understand all those elements in case you see it or you need it yourself in a VEX code. But overall, as we talked about before, most of the time I actually recommend doing this with a point WOP or with a WOP in general, because here you have the advantage of being able to use different noises directly. For example, a unified noise that has everything built in. It's a bit slow, but it has the advantage of being the most feature complete version of a noise. And here I could say I want a 3D noise. I can choose different noise types, have all the elements we just talked about, frequency as a vector, offset as a vector, down here amplitude as a vector. So all of this is built in, plus things again like the noise type or the fractal type that is much more complicated to implement in VEX. So I would definitely recommend using WOPs for noises, but sometimes again you will need noise in your VEX, and then understanding those elements is very helpful. And then of course, as a third option, is Curlnoise. And I keep saying that I use this to create directions. And I still remember it that way, because when you look at the result, if I put this onto a normal, that you get all directions in kind of 360 degrees, which is really helpful. But just to be completely precise, this is actually something you can get, like we just talked about, with other noise functions as well. So for example, an S noise, if I don't give it any input even, will also give me all directions because it's not limited to 0 to 1. So it's not completely correct to say that only Curlnoise can give you that. Other noise functions can do this too. But the Curlnoise has one advantage. A, it's easy to remember, and B, it gives you a particular kind of directions, and that is that they are non-divergent. What that means is that directions will never point directly at each other. They will always kind of float besides each other, if you will. So in other words, there will never be clumping of points. The S noise, for example, doesn't have that because it's more random, let's call it. There are cases where, I'm not sure if we can see this here, but if you would use that to drive points, for example, you would see that points are actually clumping up. Actually, let me quickly build this up so that I can show you that. So I built here a simple pop net with a grid as an input, nothing special. And then I put in a pop wrangle. And here I will just override the velocity of each point directly and say, okay, use a curl noise of the current position and turn this into a vector or a velocity. And if we look at the result, actually let's pin this, you can see that the points kind of always flow away from each other. There are certain areas where the density is bigger, yes, but they always keep flowing. They kind of never stop at any point where they can't leave. Let's compare this with another version where we use a normal noise. And this is why the curl noise is so important in the CG field, by the way. So if instead of a curl noise, we use an S noise, for example, we will see that, yes, we get random directions as well. But if we look closely, there it is. We have areas where the points out of sheer luck end up in kind of a clumped up state. So this actually keeps moving, but here you can see this is a place where the points just happen to end up in a situation where all vectors more or less point at the same area, which is again completely random. And this results in this clumping up where the points can't move further. And this can be interesting. Maybe this is something you need and then you learn something right now. But as you can see, it's not as nice. It doesn't feel very natural because the state the points are in become very static very quickly. And let's compare this again to a curl noise, which again is interesting, not just because it's a direction, but because it's a so-called non-divergent direction. And this is why it's actually the background of the pop force, for example, because this tends to be a much more natural flow of things. And here you can see they don't clump up, they keep flowing, they never diverge to particular areas. Okay, so this was a little bit of, a refresher on the whole topic of noise and randomness and curl noise with a few additional things to know. I hope it made sense and was helpful a little bit. So thanks very much and see you later. Cheers.